As usual, let's start with the learning objectives of this module. Okay. By the end of this module, you should be able to build elementary sequential circuits like latches, flip-flops, both static and dynamic. So just like we had static CMOS logic and dynamic logic, you have static flops, static sequential elements and dynamic sequential elements, right? Then you should be able to identify devices that affect setup and hold time. Okay. First, you should be able to define what setup and hold time is. That we'll do. Then you should be able to identify devices so that you can either reduce the setup time or reduce the hold time or whatever, right? Then you should be able to derive the max and min delay constraints for a latch and flip-flop based pipeline system. Okay, pipelining is probably one of the biggest takeaways from this module. Then accounting for clock skew in a pipeline system, and then analyzing time borrowing. So this is a very interesting concept that you can exploit to actually gain some time. Okay, but you should do it only with a latch based system. You cannot do it with a flop based system. Okay, so we'll look at that. And then finally, you should be able to calculate the maximum clock frequency of operation of a pipeline system. So this concept of pipelining is really not very new to VLSI, or it was not invented in VLSI at all, right? This comes from a manufacturing line where you're doing things one after the other, right? And the idea is you don't have to wait for the entire manufacturing line to be done before you start manufacturing the next one, right? But there is a much more simpler example that all of us would have seen in our own daily life, right? So let me start with that. Okay, there is a construction site. Okay, they're trying to build, the building has been built up to here and they're trying to build something from here on, right? So there are a lot of bricks which are kept here, right? Let's say there are about hundreds of bricks that are kept here, and these bricks need to be transported to the top so that they can continue their construction from there, right? So what do these construction workers typically do? They basically stand on the stairs, right? So you'll find one man standing or one woman standing like this everywhere on each stair, right? And finally you have one guy on top, right? The aim is to transport all these 100 bricks, 1 to 100, up to the first floor without dropping even one of them. If you drop it, then it's gone, right? That's the aim. So what do people do? The safest way to do this is to simply give one brick, right? And let's assume that it takes 1 unit of time for one guy to give it to the next. Okay, and all times are equal for now. So if I give one brick, then it's going to take n time units for the brick to go all the way up there, assuming there are n stairs, right? And the next brick will be given after that. This is the safest way, right? But clearly, after this guy has handed over a brick to him or her, then this guy is idle, right? So it really doesn't make sense in order to wait till the brick reaches on top. So what do? As soon as this guy is done, you send the next brick from here to this person, right? So then, by then this guy will give it here, right? So effectively what you're doing is so let's calculate the time. If we did it in that naive way, how much time would it take? Suppose there are n steps. Let's say there are 10 steps. You give one brick, wait for it to go all the way, give the next brick. So each brick is going to take 10 units of time, and total time is 1000 units, right? Now on the other hand, if I use this, exploit this fact that the guy is idle and I just start feeding a brick as soon as that guy is done, how long would that take? 100? Exactly. So if I pipeline, that this concept is called pipelining, okay, then the total time is equal to 110 units. Okay. Now this is not exactly representative of what we see in VLSI, okay, or in circuit design. The reason is we have made a very important assumption that all the delays of every person is the same, right? In VLSI, typically, it's going to happen that this guy is probably very fast, this guy may be slow, fast. So what happens is you hand over a brick, he turns around and holds the brick until the next guy can come and take it, right? So that is where the delay mismatch happens. Humans are very adept at adjusting their speed automatically, right? There is a feedback which you will adjust it so that that person comes and takes it correctly. Logic gates don't do that. They just work at a fixed delay and the output will be held until the input changes, right? So you should ensure that this guy can turn around and hold the brick and you don't give another brick by then for him to take it, because this is now an automated system. At some point, if there is a mismatch, then you will drop the brick, right? So let's assume that there is now one very old man who is very slow here, right? So what do? Each guy now has to adjust his speed so that they work at the speed of the slowest guy. So what will they do? Each one will turn around, hold the brick, and they have to hold it for a very long time, right? So this is a problem. So let's assume that these guys happen to be young guys or whatever who are quite fast, right? They can turn around, give the brick quickly, and then the old man is standing here. So what do? Instead of asking these guys to just hold this brick all the while there, you say, I'll put a pedestal here. You keep the brick here. Then the old man can collect the brick from there. I don't have to hold it for him there, right? Similarly, if there is another two people, I'll put another pedestal here, right? This pedestal is nothing but a sequential element because it is able to hold the data for you until that guy takes it, until the next one arrives, right? It's not until the next guy takes it, until the next one arrives, right? The assumption here is that pedestal can hold exactly one brick. If the second brick comes, the first brick is gone, and then you drop it and you're failed, right? So clearly, if now I introduce an element like this, a sequential element or a pedestal in between, I'm going to increase my area because I need to put a pedestal there. I need space for that, real estate for that. Then there is also a delay which is involved in placing it on that pedestal carefully, right? So you go keep it, and it's not like you can just throw it and then leave it, right? You got to come place it. So there is an overhead involved in, there is a time overhead involved in placing a pedestal like this or a sequential element. That time element, right, overhead is basically what is known as setup and hold time, right? Setup time is before the clock edge arrives, your data should be ready, right? That is to say, if I'm going to place it on a pedestal, before that old man can turn around and take it, that brick should have already been placed there. It's not like as he's turning around, you come and place the brick there. Then there's a chance again it will drop on the way, right? To ensure perfect functionality, the brick should have been placed a little ahead of time, right? And the whole time is a little bit difficult to visualize in a physical scenario like this. So we will come to that a little later, right? But what I'm trying to say is, okay, I have a pedestal here now, right? So now, how often can I send the next brick in? So this scenario is too good. Basically, where every gate has the same delay, but that's impossible to achieve, right? So forget about that. So I have to place pedestals, I have some overhead time and all that stuff. Now, how often can I feed the next brick in? So let us say, hypothetically, that I'll remove this pedestal also, right? Hypothetically, my old man is here. These guys are very fast. This last stage is going to be slow, right? So I'm going to put a pedestal here. Now tell me, how long will it be before I can send the next brick into this system here in the entrance? Yeah? So let us say each of these guys take 1 unit of time to do this, 4 guys, right? And these guys, let's say he takes 4 units and 2 units, right? So when can I send the next brick in is what I'm asking. Yeah? 3. So these guys will take 4 units of time to go and place the brick there. But how long will it be before that brick is taken off? No. So now remember that I am not going to rely on this perfect communication of things. You know, this guy giving it. So I need a pedestal in order to ensure perfect functionality. I cannot rely on guys handing over a thing like that and I cannot feed it in before that guy is done. In the sense, if this guy takes 4 units to hand over the brick, I cannot feed it after 4 units. I have to wait till this entire thing is done. So that now there is a next pedestal there. I go keep the brick there. Of course, this itself is a pedestal here. Right? So, I am going to take 6 units of time to transport a brick from this pedestal to that pedestal. Right? These guys will take 4 units of time to transfer from one pedestal to another. The next brick can be fed when? Can you feed it after 4 units? What will happen? You keep one brick at time equal to t equal to 4, right? That guy takes 6 units to take that and finish it, right? By then 4 units has come. So clearly at some point, because this delay of 6 units is larger than 4, you are going to have more than one brick on that in between pedestal, right? It will take 4, 8, 12. So somewhere 6 and then at 12 maybe you are going to have a problem, right? Or some later time, right? So therefore I have to wait for the slowest path in my system before I can feed the next data or the next brick into my pipeline system. The slowest path is basically this 4 plus 2, 6 units of time. Of course, now because I have put pedestals in there, I am going to have a further loss in time, the time that I can send it. So let's say there is a half unit delay because of placing a pedestal or a sequential element. So therefore, every 6.5 units, right, we can feed a brick into the system without anything falling or breaking. And this way, I can efficiently send, instead of sending bricks every 10 units of time, right, which I remember I told you was the safest way to do it, right? Each guy is not worrying about something coming and overwriting the existing state, right? I can now send one every 6.5 units of time. Good. So now, why not I put a pedestal here? Or why not I put a, okay, this may not make sense. Why not I put a pedestal here? One more pedestal. Now how long do I have to wait? 4 units plus something, right? Why not I just keep adding pedestal? Huh? Forget area. Let's assume you have enough area. Can I keep adding pedestals and improving my thing to the extent where I can bring it down to very, very small delay? Now, of course, this is 4 and therefore it's not. Let's say this is just 1.5, right? 1.5, if this is this 4 were 1.5 and this were 1.25, then can I bring it down to almost 1.5 plus sequential overhead? Why? Exactly. Your sequential overhead will start killing you after some time. So therefore, you cannot infinitely keep pipelining. You have to place it very carefully in order to get maximum gain. Right? Translating this to a circuit, this pedestal is basically called your capture flop. Okay? So if I want to draw this, I have a flip-flop. I'm assuming all of you have done digital circuits, so you know what digital design, so you know what a flip-flop is, right? We will come to the circuit details of this later. Then I have a combinational block C1 that's going to take 10 units of time. Okay. This guy is called a launch flop. Launch flop, this is the capture, where you go and keep it eventually. That's going to capture that data, right? And you have a combinational block that's going to have a delay of 10 units in between. If I want to pipeline this just like the way I did there, what I would do is I would now break this guy. Okay, it's like each guy now is a logic gate that has a delay, and that's 10 units, right? Of course, it's partitioned as 1 plus 1 plus 1 plus 1 plus 4 plus 2 plus something maybe, right? So I'm going to break this down into C11, put another flop in between. C12, another flop in between. That's my final capture flop. Of course, remember the same flop can be a launch flop for one circuit and a capture flop for another circuit, right? So I can't say that this is the launch and this is the capture, because for the next stage that's going to be the launch flop, correct? So the delay, the idea is delay of C1 is equal to delay of C11 plus delay of C12. And hence, what is the maximum operating frequency of this pipeline system now, or maximum time period? Just go by the analogy that we just gave. In general, I am asking. Yeah, it's basically determined by the whichever has higher delay, that is going to get your clock frequency, right? So therefore, if I have a clock period like this, if I have a clock like this, right, then what happens? My data should be ready before, in each clock period, the data and the delay should be such that data is stable before the next clock edge arrives, right? And therefore, it has to be simply the max of delay of C11 and C12 that will determine what this clock frequency is, right? So this frequency has to accommodate C11, right, plus some overhead, and C12 as well. So therefore, if you accommodate it to the maximum delay, it will accommodate the minimum delay as well. Okay. So before we go ahead and discuss more details and circuit implementation, so in this module, we are basically going to look at the design of this block. We look at various circuit implementations of a flop, of a latch, right, and then a flop. Then we will also look at how to design systems with various timing constraints using these flops and latches. So if I pipeline using a flop, then what is my operating frequency? If I pipeline using a latch, what's my operating frequency, right? This kind of thing is what I want to do, right? And of course, all of us know what a finite state machine is, FSM. You have a combinational block. I have some data here and this is some in, this is some out, and I want to feed data back from the output of the combinational block to the input of this combinational block, right? Obviously, I have to give it some delay, right? Now, question is, can I just put a logic gate here? Let's say NAND gate. Can I feed it back like this? So what is the need for the delay first of all? Because any change here will immediately affect this guy and that will come and override that state again, right? There is an immediate feedback there. So I need to delay that guy. So if I delay it, right, it means that this input will be held for some time. That's what a delay means. The input will not change until that delay, right? Even if this input changes. So if this input changes at some point, there is a delay to the gate after which this guy will change. And therefore that system can work. Question is, can I just put logic gates like that and make it work? Thing is, the delay that technically it is possible. Point is that delay through these logic gates is now a fixed number. So if I try to run it with a different, if I have to run it at a different frequency, right, then I can't do much. The advantage with using something like a flip-flop is I can now get the delay to be actually my clock period. I can define how much delay I want, right, and make my system work at different clock frequencies. Here, there is only one clock frequency at which the system can work, where you make sure that delay matches over all process corners and all that, then the system will still work reasonably. But there is only one delay and one clock frequency at which it can work, right? Of course, you have to give enough delay. This is nothing. You can't give like 30 picoseconds and expect things to work, right? You have to give enough delay so that you can do something with it. Okay? So, in order to get a delay which we can control, we put a sequential element here in between, and that's a flop or a latch, and this will be controlled by a clock. Okay, this is a state S, this is a state S1. So this is how you design counters, you do everything, right? So the need for sequential elements we have actually seen even in a digital design course earlier. Okay, I just wanted to point out that this flop is nothing but a delay element, but a programmable delay element. You can give how much of delay you want. Okay,